let's talk about functions. Everything we've done up to this point has been in the form of an equation, but now we're going to do things in terms of a function. So a function tells us, here's a definition that states, given a relation. So this is probably maybe a word we remember or not. But given a relation is just a set of ordered pairs. That's all a relation is. So you have just a collection of ordered pairs, and they're all in set notation. That's what makes a relation. It's just a set, and the set uses curly braces, and then ordered pairs are x comma y's. Then it says given a relation in x and y, right? Because it's an ordered pair, we say that y is a function of x if for each value of x in the next keyword is domain. Oops. So the domain is also a set, but this is the set of all x coordinates. So a relation has all the ordered pairs, and then domain is just looking at all the ordered pairs, but just the x coordinate of those ordered pairs. And there's also something for the y's part, which we'll talk about right now. But it says, so given a relation in x and y, we say that y is a function of x if for each value of x, again, x is in the domain, because the domain is a set of all x coordinates, there's exactly one y. So that means all the x's in the domain can only pertain to one y in the range. And the range is the set of all y coordinates. So imagine set notation is braces, and then it's just numbers, random numbers, because those are the y coordinates of that relation. So that means the values in the domain can only correspond to one y. And because of this, it gives birth to this idea of the vertical line test. Because if we consider a relation defined by a set of points, right, a set of ordered pairs, graphed on a rectangular coordinate system, so on the x and y axis, the graph defines y as a function of x if no vertical line intersects the graph at more than one point. Again, that is coming from this idea right here, how the domain can already correspond to one y. And that's why it says 1 point. Because if you have a graph that you intersect more than once, these two ordered pairs here, they are going to have the same, because they're in the same place for the x, but they are two different places for the y. So the x is corresponding to two different y values, and that does not define a function. The x can only correspond to one y. You can have one y corresponding to two x's, And that's okay. That would be a horizontal line. Because 2 points on a horizontal plane, they will have different x's, but the same y value. So that's what's nice about this vertical line test. You can just draw as many vertical lines to verify if that equation, that graph, does define a function of x. So let's do a couple examples of that. So using the vertical line test to determine if the equations define a function. And here are some equations we've looked at. So this first one we've seen is a parabola, right? Y equals x squared. And if you notice, we can make an infinite amount of vertical lines, and there will never be a vertical line that intersects this graph at more than just 1 point. So 1 point, 1 point, 1 point. That means that this equation, y, does define a function of x. So that means you are allowed to use this notation instead. So I can rewrite y equals x squared as f of x is equal to x squared. It's a different type of notation that we'll practice. It's just to let you know that that y value can be represented as this notation. That it's showing you your x value, but the outcome when you simplify that x value is you're going to be your y value. It's the same idea, just different notation and a specific definition, of course. And you can always pause this video and try these examples, but as you see, as I'm going through it, some of these you can just tell. There's no set amount of lines you have to make, but you can tell that you're only going to graph. You're only going to intersect your graph at 1 point. And this doesn't mean I have 4 intersections. This is just one line has only one intersection. This one line has only one intersection. This one line has only one intersection. This one line has only one intersection. And that's what you're looking for to tell you that this does define a function of x. So we can use our function notation. And once again, here, vertical line, vertical line, vertical line, vertical line. I didn't write this equation, but this equation is made by when y is equal to the absolute value of x. And this means, and it doesn't always have to be f of x. It could be g of x is equal to the absolute value of x, because it does define a function. Now we looked at this sideways parabola example, and here's a clear version of when something fails the vertical line test. Because right at this location, these 2 points have the same x value, but they are corresponding to 2 different y values. That would not define a function of x. It's still an equation, but it is not a function. Similarly, we'll eventually talk about a circle. This is a circle that's centered at the origin with a radius of 1. And the goal is not to make a vertical line where you think this will actually pass the vertical line test. You're trying to make a line that shows that it fails. And the moment you find one line that intersects your graph more than once, it could be 2, 3 times, as long as it's more than 1, it is not a function. That doesn't mean it's not valid. That doesn't mean it's not useful. Circles are going to be extremely useful in trigonometry. But here, it just means it just doesn't define the definition of being a function. Now that we saw a little bit of how to verify what equations visually are functions or not, let's continue looking at this notation. So our goal is this first example of evaluating. And it just switches it up. Normally we would have said let x equal -3 or let x equal 2 or let x equal 0. And it's still doing that because what's inside this parentheses is x. I'm saying that x has to equal -3. So what does that mean? I'm substituting my x for -3 not only in my function notation, but on the entire right-hand side. And something I like to do before I substitute is I like to put everything in parentheses, especially when there's a negative, because I'm not sure how they're going to behave when it comes around powers. Because -3 squared is going to give me +9, and then 2 times -3 is going to give me -6, and that's going to simplify to 3. Now, if I didn't write those parentheses and I would have written just -3 squared, this is equal to -9 actually. Because the square pertains only to the 3, and you have to treat this negative as like it's saying -1 times 3. Versus here, that negative is in the parentheses, so the square is applied to the entire number. And similarly, I just continue. 2 and 2. 2 squared is 4. 2 times 2 is 4. 4 plus 4 is 8. And then 0 and 0. Again, makes everything much quicker if you just write in parentheses so you don't make any mistakes. But of course, 0 squared is 0. 2 times 0 is 0. So these are 0. If you want to continue trying more values, pick any number you want so you get used to this notation. Now, what makes these problems challenging is when you start evaluating these functions. For example, another quadratic has a square, right? That's the indicator that this is some type of parabola. The tricky part is when you start doing evaluations with things that are not numbers. For example, this first one says to input just a. Replace your x with a. And that's going to just simplify to 3a squared plus a. So it's the same exact variables and powers. I'm just replacing the x value with a. But then this following one, I want to substitute f of a plus h. So a plus h. And like I said, because I know I'm substituting something large, I already start doing the parentheses to plug them in. But here, we have to take a little bit of time. Because on the right, even though this has an equal sign, the right-hand side, we almost treat it as an expression. Which means we should probably take care of this square first. But I just want to make a quick note. For rules of exponents, when you have two terms being raised to some power, this does not mean to multiply each term by that or apply the power to each term in the parentheses. It means to expand that power however many times is necessary up to your power. Students may sometimes get this rule mixed up with the multiplication rule of powers that says when you have a product within the parentheses being raised to a power, you're allowed to distribute that power. Now, it's common to see how these two can get mixed up. that they couldn't be further apart from each other. And one more rule just to keep in mind when you come across certain problems. When you multiply, since we're dealing with more variables, when you multiply two variables that have the same base but different exponents, you're allowed to combine them together and add the exponents. And there's other things you can do, other rules, but for now, these are great because the very first step, I have to apply the first rule that I talked about. Because this does not mean distribute the power to both. You absolutely do not want to be doing that. But it does mean, I'm going to just do a little bit of side work up here. Hopefully it doesn't look too crammed in. But how do I take care of this a plus h squared? It's going to be a plus h times a plus h. And now I just have to take my first term, distribute it to both as a distributive property, and take my second term and also do the distributive property. Now, some of you might remember FOIL, which is first, outer, I think it's first, outer, inner, last. But just looking at this example, I can just take one term, distribute it through, take the second term, distribute it through, and we're multiplying from left to right. With that said, if I multiply a times a, those are the same base. The exponent for a here is 1, and here is 1. So that means this is going to become a squared. And then a times h is just going to be ah. Then h times a is ha. Plus h times h is h squared. Now at first glance, it doesn't seem there's anything to do. But if you look at these two terms, you have to make a quick note that a times b is equal to b times a. That even though these first two might look different, they aren't. And what I mean by different is because it's AH and HA. These two are exactly the same. You would just write A squared. Let me just highlight this real quick. So A squared plus 2AH. Now you do have to pick. You can't put AHHA because that's going to create A squared plus H squared. And this is not a multiplication symbol, it's an addition. So that means I'm going to add the coefficients, which could be 2, and just choose one of the variables to use. Plus h squared. Because I did all that work on the side, all I have to do now is take 3 times, and then this entire expression I just calculated. And then that second term isn't doing anything. It's just going to be a plus h. Now, hopefully you guys see, I can do this distribution, which is going to be 3a squared plus 6a plus 3h squared plus a plus h. And that's all. Normally you would try to condense this if possible. But that is the idea of this example. does involve a little bit of algebra, but definitely doable. Let's do another one. So here, once again, we're going to be plugging x plus 2 in, x plus 2. Now, luckily, this square part appears so many different times. So it's going to be good to slightly memorize that x plus 2, it was a plus b, but this is x plus 2. I'm still going to apply the same property. X times x is x squared. X times 2 is 2x. 2 times x is 2x. And 2 times 2 is 4. And then that's going to give me negative x squared plus 4x plus 4. And I can distribute this negative here. And that's going to give me plus 4x plus 6. And lastly, distribute this negative through. And that's going to give me negative x squared minus 4x minus 4 plus 4x plus 6. 4's cancel. I'm left with negative x squared I made one slight error really quick. This shouldn't have been a 6, that should be 8. And the reason is because negative 4 plus 8 is going to give us plus 4 next. So negative 4 plus 8 give us positive 4. And this is the difference quotient for h of x plus 2. So try to go slow. Don't rush these examples. Let's do a couple more. We'll apply this one. So here, you have to plug in an entire fraction. 1 over x plus 2. But you have to make a quick note as well. And when we divide fractions being raised to the power, you're allowed to apply that power to both. So what's that mean? I'm going to apply that to a square, and I'll apply that to that x plus 2, which luckily we just did x plus 2 squared. So this should go a little quicker. It should be negative, and then it should be negative 1 over, let me write this a little bigger. It should be negative 1 over x plus 2 squared. And then plus, and if I distribute my 4, it's going to be 4 over x plus 2. And if, so it goes to simplify further, I know to be able to add fractions, I need the same denominator. So this denominator just needs an x plus 2 and an x plus 2. This will simplify to negative 1 over x squared, quantity squared, plus, I'm going to distribute this 4. That's going to be 4x plus 8. All over x plus 2 squared. Now, when you add fractions, your goal is to get the denominator the same so that you can just add the numerators. The 4x has nothing to do with the negative 1, but the negative 1 can do something with that 7. So it's going to be 4x plus 7 all over x plus 2 squared. And on the next ones, we will talk about the difference quotient. It's going to be a lot of evaluating. I'm going to evaluate into the function, and I'm evaluating into the difference quotient. We'll do that on the next one.